Okay, good. I see people are filtering in, so I'll give it just a minute or two before we get started.
Do you want me to start sharing my screen?
Sure. Yeah, you can go ahead and do that.
I think we're gonna be, wait, and I wanna make sure that I'm sharing the right one actually. Share, and now. So do you see the right one or the wrong one?
It looks right to me.
Okay.
I think Professor Lyons was able to join, but the name, at least on my computer, appears wrong. It's under Dominika Simaki.
Maybe we can rename. Linus, hi.
Hi, morning.
Try to rename your screen because I sent you my link for the webinar, and so you appear, your name appears to be from Nikki too, which is, I mean, it's okay, but
Oh, really?
Yeah.
I think if you go on the participants and then find your name and click more, it has an option to rename.
Yeah.
Okay, well, while we're getting that situated, I can get us started. Hello, welcome everybody. Thank you for joining us today for the GEER webinar. If it's your first time with us, or if you haven't heard of GEER before, GEER stands for the Geotechnical Extreme Events Reconnaissance Association. My name is Elliot Nichols. I'm the GEER recorder and also a PhD student of the director of GEER, Professor David Frost. Just before we get started, I wanted to go over a few housekeeping items. This webinar, just like other previous GEER webinars, will be recorded and it will be posted on the GEER website as well as the GEER YouTube page, which I can link below in the chat. If you have questions during the webinar, please type them in the Q&A tab at the bottom of the screen. If it's a brief question, some of the speakers might be able to answer it directly during the chat or in the chat during the seminar, but there will also be a lot of time at the end of the webinar for questions, and we're hoping to be able to get to everything that's asked, and we'll have a little moderated session then. Lastly, I'd like to acknowledge the support of the National Science Foundation and the NSF Program Director, Giovanni Biscontin, who has been a major asset to GEER over the years as we've deployed teams to study geotechnical impacts from natural hazards such as the magnitude 6.9 Taiwan earthquake from September, which is the subject of our webinar today. We have a wonderful group of speakers that you can see here to discuss the deployment stemming from this event. So with that, I'm happy to turn it over to our first speaker, Professor Dominiki Azumaki. Dominiki, I think you can take it away.
Thank you, Elliot. Good afternoon, everybody. I am Dominiki Azumaki. I'm a professor at Caltech, and with Benjamin Mason, we were the co-leads of the 2022 magnitude 6.9 Chihshang earthquake sequence. So on September 17, 2022, a magnitude 6.5 quake shook the southern east end of the island of Taiwan. This is shown here on the left. The quake nucleated about 10 kilometers at depth, so shallow, and was widely felt across the island. 16 hours later, a magnitude 6.9 shallow quake followed, nucleated further north, again at 10 kilometers depth, and caused serious damage in the region. Clear elongated rupture emerged from the damage that was caused by the second event. And this slide shows the ground motion map from the Central Weather Bureau that operates, among other networks, the Taiwan Strong Motion Instrumentation Program Network, which comprises about 700 free-field storm motion stations. Taiwan is the result of the ongoing collision between the Eurasian plate and the Philippine sea plate. The collision occurs in a double inverse subduction context. In the southwest, the Eurasian plate subducts beneath the Filipino plate, whereas in the northeast, the Philippine sea plate subducts beneath the Eurasian plate. The black arrow here indicates the direction of convergence between these two plates that have an estimated rate of about 82 millimeters per year. The longitudinal valley where the event primarily was felt was located between the central range and the coastal range on the right here. It's about 150 kilometers long and has a maximum width of 7 kilometers. The area is the plate suture boundary between the Eurasian plate and the Filipino Sea plate. The red lines show the major fault traces that are located in the longitudinal valley that are indicated by the Central Geological Survey. The longitudinal valley fault on the right is an east dipping, obliquely slip reverse fault, along which the coastal range is rising rapidly. The creep is maximum about 3.5 centimeters a year, and it moves towards the central range. On the other side, the less prominent central range fault is a west dipping reverse fault, and the central range fault is blind in the south, where the event was nucleated and was inactive until this past decade, because of this inactivity, the fault was actually not included in the official active maps that was issued by the Taiwan Geological Survey in 2021. The two events of the foreshock and the mainshock of the 2022 Chihshang sequence nucleated the southern end of the valley. The centroid moment tensor solution shows that the events nucleated on the central range fault that ruptured part of the strike slip Uri fault to the north, which is a branch of the central range fault. The distribution of the aftershock sequence showed wide activation, as you can see here on the left of the central range fault, to the left of the valley and underneath the mountain ranges, but it also, the shocks likely triggered some part of the longitudinal valley fault, as you will hear later. So the United States National Geological Science Foundation funded GEER Geotechnical Extreme Events Reconnaissance Team arrived in Taipei the 15th and the 16th of October 2022. We delayed our arrival because of the quarantine that was imposed by the Taiwanese government. And we traveled to the affected region on the 17th of October. We conducted 5 days of fieldwork. The GEER team, which included 8 US-based members, was hosted and accompanied by a team of geologists, geotechnical engineers, and researchers from Taiwan's National Center for Research in Earthquake Engineering, NCRE, as well as a team of remote sensing experts from National Xinan University. Given our close-knit field operations, we collectively refer to the US team as the Taiwan Field Reconnaissance Team as the GEER team. We split our team into 3 sub-teams to maximize our field operations. We had the ground failure team, the bridge team, and the surface fault rupture team. The locations that we inspected, indicated here on the right by the different signs, are shown on the map. And we also benefited tremendously from the dense seismometer network throughout Taiwan, of which we had access to the time series. And we have arranged our presentation with respect to the observations of the sub-teams. So without further ado, the first part of our presentation will focus on surface rupture observations and will be given by Brian Gray, who's a principal geologist at Lattice Consultants International. Brian, take it away.
Thank you, Domniki, and good afternoon. If you can go to the next slide. Thank you. So our approach for the reconnaissance for the surface rupture, knowing that the earthquake occurred about a month prior to when we were there, that the local Taiwanese geologists had done quite a bit of mapping already to map the rupture. So we focused primarily on some engineering specific aspects of the rupture and focused on a few key locations. One of the very unique things about this earthquake was the fact that the fault ruptured, the fault that actually ruptured, produced the earthquake, was a central range fault, but much of the surface displacement, especially in the southern half, actually occurred on the adjacent and oppositely dipping longitudinal valley fault. So understanding triggered rupture is an important component of fault displacement studies. So that was a key focus of this effort. So we looked at, we wanted to know what the structural interactions were with the surface rupture, what was the rupture width, distribution, of course, triggering of the deformation. So we also looked at not only how the longitudinal valley fault ruptured, but also potential ruptures for hanging wall structures in the longitudinal valley. And then the surface expression at sites with historic ruptures. So this event was also unique in that there are several places that ruptured in 1951. And normally as geologists, we think of of fault displacement occurring at scales of millennial time scales, or at least hundreds of years. But in this case, the Longitudinal Valley, because the fault produces or is slipping at such high rates and produces fairly small magnitude events, so magnitude 6 and low magnitude 7s, we get very frequent earthquakes. So we had repeated ruptures. So this map just shows the distribution that from the Central Geological Survey that documents kind of all the ruptures along the section. But again, we focused at a few locations, one at Fuli, and then at Dongli to the north, and then also at Yuli. So we'll continue the next slide, continue to Fuli. So this is a map of that our drone team surveyed, that our drone team collected. And you can see that the rupture is quite linear through the town. At this location, even though the fault is uplifting at rates of probably about 15 millimeters a year based on terra studies, the fault here is actually, the expression was almost pure strike slip. In most cases, we saw anywhere from about 15 to 20 centimeters of displacement, a left lateral displacement. But in some cases, it looks like we had more, probably in the order of up to 50 centimeters, maybe more. As I'll show in a future slide, we have, there's some uncertainty. Some of the offset structures are displaced up to 90 centimeters, but the fault here creeps at a very high rate. So some of that displacement could be inherited from, that predates the rupture. So in general, for the most part, the displacement occurred over a width of about 3 to 10 meters in town. Next slide, please. So this is an example of where, again, we were here about a month later. So a lot of these failures had already been repaired, but you can see the margin of the road and the sewer lateral, which is on the right side of the road, was offset about 90 centimeters, and the wall is damaged. The wall is displaced adjacent to that. So some of that displacement occurred is co-seismic, and some of that probably predates the rupture on the fault for this event. Next slide, please. And this is just, although this is not rotated in north-south direction, this is a drone image that it's not georeferenced, but we can see that these are rice rows. The row spacing is typical row spacing is about 25 centimeters. And displacement of the rows themselves is about 2, give or take, a half of a row. So we're looking at about 50 centimeters maybe of displacement in the field just to the south of the city. So if you go to the next slide, this is a reconstruction of that. And it's a little bit blurry with the presentation here, but there's a really nice marker at the kind of bottom right corner of this that restores very well. And then for the most part, things restore pretty well across the whole field. Next slide. So this is another site. It's about, I think about 10 kilometers, maybe a little bit less to the north, where instead of the fault being expressed as a really clearly defined structure with a narrow zone that's on the geomorphic escarpment, here the scarp is actually along the roadway, along the left-hand, kind of left third of the image here, or close to it. But most of the surface rupture occurred well to the west in the hanging wall, and lots of little short discontinuous scarps with about 10 to 15 centimeters of uplift on each strand. And so the total zone width is about 300 to 400 meters. There were a lot of complex ruptures through the roadway on the left-hand, kind of upper left-hand side of the image here. I won't get into details, but this would have been a place where if we were designing a structure or had to define parameters for displacement, we would have probably had a very difficult time determining where the rupture was actually going to happen, because we would have put most of the displacement at the range front or at the geomorphic escarpment near the roadway. Let's see, next slide. So this is just a few photos of the rupture, showing the small displacements, these very small scarps. You can see in the upper right image, there's a big concrete retaining wall structure, and that was a deformed about 10 centimeters over the width of about 10 meters. So not much, it wasn't even clear that it was cracked at first without lots of detailed evaluation of the structure. Next slide, please. So this is an example of the interactions of structures and the faults themselves. So this is one of the faults at Dongli, where we had a little bit of shortening, about 15 centimeters of uplift. Fault strand actually went through on the image to the right. It continued up basically beneath the mat foundation of the building in the upper right hand of the image, and then continued across the roadway and then up to this wall with about 15 centimeters of slip being expressed in the concrete and cobble retaining wall. And next slide. So this image is looking the opposite direction from that wall where the fault ruptured beneath the building. So it cracked the outside, the exterior of the structure, and spalled plaster off the walls, and also there are large cracks in the roof and coming up through. So, but the fault didn't rupture. The structure actually doesn't have any cracks where the fault projects through. The cracks occurred where there are weaknesses, such as that doorway off to the left there. That was a common theme that we saw, that the fault obviously finds the plane of weakness, and ruptures get very complex when it interacts with structures. Next slide, please. So this is an example of rupture in Fuli, where the fault ruptured down, essentially found the sewer lateral and ruptured down the sewer line, pure strike slip displacement, and then the rupture became complex. So in the image to the right, that's the rupture distribution. The fault continues kind of up to some structures in the upper right-hand corner. And there are two buildings that I'll show in the next slide that had, or sorry, the image on the left shows those two buildings actually. One of them, the first one, the one in front, was yellow tag, and the one in the back was red tag. And if we go to the next slide, so there's just another view of the surface rupture continuing toward that structure. So the rupture went around left of the building in front, which was yellow tagged, and then the building behind, which is essentially hidden. The fault rupture went beneath the building, and that would there's a right step in the fault system here, so that would be a restraining geometry, and there was uplift. If we go to the next slide, there was actually uplift on the structure where we had relative substance in the street in front, and also relative substance in the back of the house. So the whole it appears the whole structure lifted up, and so the back of the house actually kind of separated, and so this structure was actually red tagged. There was some collapse in the back of the house as well. So this is an example of where a complexity in the fault produced some unique displacement and also some unique damage. So next slide. And so I mentioned earlier that there were repeated historic ruptures on some of these faults. And in this case in Fuli, so this is that same location I just mentioned in Fuli, where we have on the left, where you can see our team members are looking at the fault. That's where the main September rupture occurred. So there were about 18 centimeters of left lateral displacement that went down the street along the sewer line. But you'll see there's also fracturing on the right-hand image, and that is represents about 5 centimeters of pure shortening on the far right-hand side of the right-hand image there. There's a crack in the street. So just to the south or towards us, Domniki, on the right of the yellow line there. Yeah, that right there. So that actually represents, from what we were told by the resident who lives in the house just off this image, that displacement occurred during the 2022 March event. I think it was a magnitude 6.5 on the Longitudinal Valley fault that produced a small amount of creep on the fault. So here we have two different styles of displacement on the same structure occurring at different locations during events separated by about 6 months. So it's very unique. Let's see, next slide, I think we'll talk about Yulee. So yeah, Yulee. So this is another place that ruptured in 1951. We had, in 1951, there was about 10 to 40 centimeters of displacement, left lateral strike slip displacement through the town. A number of the places that we visited had ruptured previously, and there were photos documenting that. And the rupture here was also very similar. In most cases, about 20 centimeters. Next slide. So just in summary, rupture complexity and distribution was highly variable. In places where we saw strike slip displacement, rupture was pretty simple and well-defined and would have been easily located based on geomorphology, whereas at Dongli to the north, where rupture was in the reverse sense, it was very distributed, small displacements over an area of several hundred meters. Would have been very difficult to define from a geomorphic expression or paleoseismology. It appears that the sense of slip is very sensitive to fault strike, as we would expect. Just an observation that confirms that. As I mentioned, the fault often took the path of least resistance through structures, so around foundations, joints and retaining walls are the things where it seems to always find the path of least resistance. Typically on the Longitudinal Valley fault, we saw displacements of several tens of centimeters. About 50 centimeters is probably the best estimate for net displacement, for lateral displacement for Longitudinal Valley fault in Fuli. And then ruptures from Fuli and Yulee were quite similar to reports from 1951 that were compiled back by Rushu and others in 2007. I should note, though, that there were also places that are very different for this rupture. There were some larger displacements near Dongli, maybe up to 1.5 meters during 1951 that we certainly didn't see here. So thank you.
Thank you, Brian. So with that, we will move on to the next part of our presentation. The ground motions and tectonic offset given by Gregorio Zavardiave, who is a postdoctoral researcher here.
Thank you, Dominiki. Next slide, please. So to evaluate the ground motions, we were given access to 4 strong motion datasets in Taiwan. And from there, we were able to use 25 3-component time histories for the major event, the 6.9 Chihshang earthquake, and 40 for the smaller one, the 6.5 event. The reason that we have more recordings for the smaller events is because some of the stations were clipped during the main shock. And additionally, we were also given access to the offset estimated through the GPS stations that were recorded the displacement 1 day before and after each earthquake. From them, we have 124 for the 6.9 earthquake and 41 for the smaller event. Next slide, please. So we started by being provided the instrument corrected time histories, and next, please. And we performed a baseline correction that maintains the permanent tectonic offset at the end of the record using the Bohr et al. 1999 and 2002 procedures. And then we used the standard NGA peer framework to do further processing, filtering the ground motions, and applying some additional baseline correction. So from this procedure, we got 2 data sets. Next, please. And one more. Thank you. Which will be provided, which together with the code that we used for baseline correction, we will provide it as an electronic supplement from the GEER report. Next, please. And the exciting thing about these 2 events is that they fill some of the gaps in the available empirical datasets, in particular at the moderate to large magnitude range for small distances. And here we have stations that were from 1 kilometer to 10 kilometers away from the rupture. here we can compare the tectonic offset that we got from the strong motion stations shown with the black arrows and the tectonic offset that was inferred from the GPS network shown with the green and blue arrows. So those are the permanent and the mobile deployment. And it's important to mention that those two datasets were processed separately. So next, please. So we were excited to see that using this baseline correction procedure that I just described, we were able to get consistent estimates with the GPS stations. And in terms of some of the findings, we found most of the offset occurring at the middle and the northern end of the rupture. And in particular, on the central range fault hanging wall, we saw 1 meter of right lateral slip and 1 meter of uplift induced by the change in the strike. And on the longitudinal valley fault hanging wall, which is the one that Dominique is currently showing, we observed shortening, and the order of that was 90 centimeters close to the rupture. But interestingly, we also saw in the order of 30 centimeters of shortening, even at 40 kilometers away from the rupture. Next one, please. For the 6.5 event, the amount of displacement was smaller due to the smaller size of the earthquake. And the spatial distribution had the opposite trends, where most of the tectonic offset was observed at the southern end of the rupture. The maximum tectonic offset that we inferred from the strong motion dataset is about 20 centimeters. Next, please. Thank you. For the peak-to-peak velocities for the main event, we found, next please. We found strong pulses perpendicular to the rupture in the direction that the rupture propagated, that were induced by forward directivity. But also we found large velocity pulses parallel to the rupture that accommodated the permanent slip that we saw in the two previous slides. Next, please. And here, these are strong motion records show some of the key findings that we just described before. So for the first one, this is a station that is just 3.5 kilometers away from the rupture, but it's close to the epicenter. And we can see that, and we can see in the displacements, the permanent tectonic offset that was observed at the end of the strong motion shaking. Whereas for the strong motion record in the middle, that's again 3.5 kilometers away from the rupture, but this is in the direction that the rupture propagated towards. And here we can very clearly see in the east component the two-sided velocity pulse that was the result of forward directivity. And the east component is aligned with the fault normal direction. And then last, we can see on the third set of figures, this is a station that is on the hanging wall of the longitudinal valley fault, but 16 kilometers away. And interestingly, we observed that even at those large distances, we had the permanent tectonic offset, which was in the order of 24 centimeters for this particular station. We also compare the process strong motions with empirical ground motion models. Here we used the NGA-West2 ground motion models for spectral accelerations. And we observed that the ground motions were below the average for short period motions, whereas for moderate and for medium and large period motions, the ground motion observations were either average or above average. For the PGV, as we saw earlier, we observed very large peak ground velocities that were above the NGA-West2 ground motion models. And for the duration, we saw both the D5 to 75 and the D5 to 95 that is shown here that were average or slightly underestimated by a shallow crustal ground motion model. And those are the findings that I just described. And one other point is, because we are in such a close proximity to the rupture, all these comparisons were very sensitive to the finite rupture geometry that we defined to calculate the various distance metrics. And with that, I think we will pass it to the next speaker. Thank you.
Thank you, Greg. The next speaker now will talk about the infrastructure performance, focusing on the performance of bridges along the valley, so along the suture. This Trevor Carey, who is an assistant professor at the University of British Columbia. Trevor, take it away.
Thank you, Dominiki. Next slide. As she mentioned, I'm going to be really talking about the impacts to infrastructure today, specifically bridges and retaining structures. I'm going to be focusing on kind of the most main and kind of extreme events that we saw, but in the final report, we'll have additional findings that you can read that you just don't have really time to go through today. In the prior section, Greg talked about the 6.5 and the 6.9 events. Based on our discussions with INCRE and local members of the community, really the damage that I'm going to be showing you today, we primarily are attributing to that 6.9 event. That's not to say that we had systems that were partially damaged during that initial 6.5 earthquake, but just given how closely these events occurred, we don't have that real true damage estimate of that. The infrastructure team, with the help of INCRE, identified 8 damaged bridges, with all those structures being about 2 kilometers within 2 kilometers of the central range fault. Given the topology of the valley, the longitudinal axis or the direction of travel of these bridges was really perpendicular to the rupture and the fault itself. 2 of the 8 bridges had multi-span failures, and which is really going to be the focus of today's presentation. One of those bridges is shown above in figure 3. We've also observed minor to severe damage to lateral earth retention systems, and I'll touch on those failures today. In photo 1, it's a little hard to see, but there's a large crack in that wall, that green wall there. And then photo 2 is a LiDAR view from our LiDAR team of one of the bridge approaches that I'll spend a few slides on in a few minutes. In the bridges that I'll be speaking about today, we really didn't see any surface fault rupture that crossed the spans itself. But as Greg showed on the previous slides, we did have ground motion recordings that indicated that we did have permanent movement or offset. Next slide, please. Here's a map showing kind of the, one back, there we go. Here's a map showing the epicenter of the earthquake, which is given with a star, and with the rupture propagating north along the valley, which is shown with that red arrow. I give you 2 ground motion recording stations. This is stations that Greg provided to me. And you can see we have the acceleration and the velocity and the displacements at those stations. We had, again, what Greg mentioned on the previous section, we had kind of large velocity pulses that increased along the valleys. The PGV and the southern station there was about 57 centimeters per second, and that increased to 91 centimeters per second in the northern station. To provide some perspective on these numbers, I took a look at the NGA West 2 database, and there are 50 records with PGVs greater than 75 centimeters per second. And with 9 of those records from the 1999 Chihshang earthquake, so about 20%. On the right-hand side are the location of the bridges that we'll be talking about today. I'll be speaking today about the London Bridge, which is on the south, that had several span failures, the Yulee Bridge in the middle, and the Galileo Bridge, which is in the north, which was the most heavily damaged structure we looked at. Next slide, please. The Linton Bridge was the first bridge the team visited. This bridge was built in 1982 and was a reinforced concrete deck girder. There was 15 spans, with each span being about roughly 30 meters for a total bridge length of 450 meters. So shown in figure 3 down below is actually a drone view of the bridge, looking at kind of the damage that we saw. Of those 15 spans, we saw 8 failures. And by the time that we arrived on site, a lot of that had been already deconstructed and cleaned up a little bit. We suspect the cause of failure was a bridge girder unseating, but instead of the spans widening and that girder falling straight down, we suspect the velocity pulse actually pushed or shifted the girders along the pier cap. And you can kind of see that in figure 1. In figure 1 there, you can kind of see there's a little plant on the very left-hand side of the girder, and the pier cap, and we suspected and kind of measured that girder was right next to that plant. And as the earthquake occurred, and the velocity started to push those girders. It pushed them over across the pier cap. And you can see in figure 2 how close that is to the edge of that pier cap and that last span that did not fail. We suspect that when those girders fell off, that caused a bending moment of the base of these piers, and that bridge system couldn't support it, and then the spans toppled. We didn't find any shear keys that would kind of restrain that lateral movement from the piers that were undamaged or hadn't failed. Furthermore, just kind of a general note, this is an alluvial environment, and we didn't observe, nor was it noted in the initial inquiry report, that there was ground failure that would suggest liquefaction or any lateral spreading. Next slide, please. Here are several other photos from the same bridge. Photo 1 is looking from the abutment. You can see compression there at the abutment end, and you can see there's offsets in the spans in front of the abutment that didn't necessarily fall, but that still have some kind of failure. And photos 2 through 6 are the views of the concrete piers that fell during these span failures. These piers were embedded about 1 meter below the ground surface, and the soil is consisted of really fine-grained materials from silts and clays to cobbles and boulders. In photos 4, you can see there's a kind of, it's a little hard to see, but there's a concrete pad, and this was kind of a common thing for several of these piers. They were sitting on these concrete pads, and it was just the only thing connecting was the steel reinforcing and perhaps a cold joint. I should note a lot of these bridge systems that we'll be looking at today, one of the primary concerns of failure is actually scour from the high flows that you can get along the rivers. Next slide, please. This is the Galileo Bridge. This was the located furthest north in the valley, and this was the kind of the furthest north bridge that we looked at. The structure was built in 1991 and was a pre-stressed concrete bridge. The bridge had 22 spans and is about 879 meters, with those spans supported by piers as well. Based on photos from inquiry and kind of our observations once we arrived on site, we believe that all the 22 spans had failed during the earthquake. Shown in figure 1 is a photo that I took looking at kind of those failed piers from one of the embankments. In photo 2 is a drone shot from our great drone team as well, and you can see each one of those little bumps. That's one of the piers that had failed. And in photo 3 is another drone shot taken by Zola Zhao right after the actual event. You can see the bridge deck in relation to everything before had been cleaned up. Next slide, please. Here's a close-up of those piers. You can see that there is more reinforcing steel in these structures compared to the first bridge, but we still see that plastic hinge developed. And the 1 to 2 undamaged piers shown in figure 1, it's a little right at the very end there. We checked and we couldn't see any shear keys or bumpers that would hold those girders in place. And we suspect that there was a similar failure as the first bridge, where once the girders kind of were pushed off the bridge, it brought the piers down with it. Both of these bridge failures are important because it's a kind of maybe a non-typical unseating failure. Instead of the bridge deck just falling directly down in the spans, the failure or unseating these bridge girders took out the supporting piers, which would need to be replaced during post-earthquake event recovery, which would really prolong our earthquake recovery time. So this entire structure will need replacement. Next slide, please. I briefly want to talk about the Yulee Bridge, which was located between these 2 failed bridges just outside of Yulee. And this was a failed bridge. There's actually 2 bridges that were parallel, but this does provide important insights into why the systems that we did see failed. Why we see that. So these were parallel bridges, and they were reinforced concrete deck girders. The south span was built in 1977 and the north in 1994. These bridges were operational when we visited, and they had really minor damage. In photos 2 through 4, I've circled these little teeny bumpers, and these were sacrificial elements that held the girders in place. In photo 3, you can see an intact bumper, and in photo 4, there's one that has failed and it needs replacement. These were kind of elements that were supposed to hold the girders in place, allow a little bit of movement, but not allow complete movement where we get unseating and potential failure of the piers. The question then becomes, why did these bridges have bumpers and the other ones we looked at did not? And the reason for that is these bridges themselves actually cross the suture of the Eurasian and Philippine Sea Plate, which you can kind of see there in photo 5. That's a little diagram of it. And we suspect that these systems were developed and designed to accommodate large movements because of that suture location. Next slide, please. We observed minor to major damage in lateral retention systems, but in the last few minutes, I'm really going to be talking about one of the approaches for the Galileo Bridge. These systems were concrete gravity walls with fill, and I suspect that fill was sourced from the nearby river, and the gravity walls were nearly 2 meters thick at the base. Photo 1 is another view from our drone, and you can really see that cracked roadway and the slumping of the actual road itself along the sides. And images 3 through 5, I show kind of the depth of the crack and the movement, which were well over 1 meter to 2 meters at some point. In figure 4, you can see Estefan there taking the survey of the damage, but there's a little red line there that shows the original location of the roadway itself, and you can see that it moved about 1.5 to 2 meters there. The soil that constructed these systems had particle size ranges that are probably not typical of the approaches that we'd see here, and that could have made compaction difficult to get good compaction. We're assuming that these systems were above the water table, but hydrostatic pressures may have played a role in some of the deformations we saw. Next slide, please. This is the same approach, but we're looking at it from the kind of the other end where the roadway, not at the bridge end. And you can see from figures 2 and 3, that's the slump there that's given in figure 1. There's a little slump at the end. This approach actually had an access tunnel through it, which provided a datum to measure deformations or displacements of the actual wall itself. And figure 4 is looking through that access tunnel, and you can see it's not aligned with the wall itself. The concrete, the access tunnel was actually concreted and secured in the ground, and we assume that that's the original location of the wall in the system, and then the walls actually moved around it. And finally, shown there in figure, the top of figure 5, or yeah, excuse me, you can see that, excuse me, the displacement in figure 5 is about 16 to 17 inches. And finally, in figure 6 there, you can see there's a sinkhole, and the pile of that material is actually showing the bottom of figure 4. We took a look at that, and we could see that material was coming from around that tunnel itself, which was very loose material. Next slide. In my last few minutes, just kind of some takeaway observations from this, is we saw that the bridge girders really were unseated laterally off the pier caps due to that large velocity pulses. This caused failure in the supporting piers, which could prolong recovery times because those piers would actually need to be replaced. These failures could occur in bridges in the US and Canada along faults that may have potential directivity, and it's something that we should study further so we can minimize that type of damage. We saw large movement in gravity walls. Even smaller walls, we saw movements that were surprising to the team, partly because those systems were also engineered. And then finally, ground failure really wasn't observed at any of these locations. This could be a product of the soil gradations we were looking at, from kind of the silts and clays all the way to cobbles or boulders, or there may have not just been enough cycles of loading, or likely a combination of both. We're expected to see some kind of localized failure, but we didn't see many manifestations that would suggest liquefaction or lateral spread. I'd like to thank you for your time, and happy to answer any questions you may have.
Trevor, thank you. And I apologize, I try to point out different slides, and then I end up moving slides back and forth. The last part of the presentation will be given by Kolong Wang. He's an associate professor at the National Tsinghua University, and he will talk about, he was the team lead of the drone campaign that followed along with was part of the GEER team and followed us along the move from team to team. Observation of bridges and ground failure, as well as fault deformation, and he will give us an overview of the drone observations of failure of the campaign. Linus, take it away.
Okay, thank you, Dominique. And I just upgraded to full professor 2 weeks ago. So, okay, that's no problem. Thank you. And I would like to show you the drone size, and thank you, Ankri, invite me to use the drones to reconstruct the model of the earthquake. And here we have several drone sites. You can see the map. We have 4 bridge and slope and rock fall. And some of the slope failure part is within my study, but not totally failure. So we'll see some of them. And next slide, please. And also we all the data we reconstruct the model, we put it in 3D wave viewer, so you can see the the west side here by yourself, so you can easily to measure in the distance and the height of each slide. And I just some of the because it's open source code, we use a Chinese character, so you can I see the left hand side we have a translate to English, so you can use any the system control by yourself. Next slide, please. And the first one is the fault rupture is the left hand side is a fully one, and I think a previous presenter already presented fully town, and then the middle one is a Dongli, and especially in the inside there's a sports field of Dongli at junior high school. So you can see the upper right, the sports field. It seems that very clear, should be a very horizontal sports field, but it looks like it's 0.6 meter elevation change. I was wondering my student do the drones incorrect, so I went back there and on November to check measuring with GPS, and unfortunately the measurement is correct. So the elevation difference between the sport field is 0.6 meter. That's correct. Next slide, please. Okay, that's next slide, please. And the fault rupture 2 is already north of the rupture, or not, but this side shows the embankment failure, and you can see the left side we have also image and DSM, and you can with the hill shaded image is very clear the crack on the levee. And when I back to there, because this side we don't use the GC ground control point, so I went back there on November to measure in GPS, so we produce a more accurate image later. So you can see the right hand side, the bay you already fixed in 2 months. Okay, next slide, please. And the third is the Changliang Fort. I believe you went here on October, but you don't. I'm not sure because previous slides we presented you don't have this one. So I have 1 day, so I have enough time to go to here because it's already 2 months after the earthquake. But you can see the upper right hand part is still keep the rupture. For lower right part, there's some excavator. There's a excavator already digging the surface. They're trying to find how depth the rupture show in the surface rupture. This site is between Yuli and Dongli. Okay, next slide. So you can see that the elevation difference of the rupture from 2 points. The lower part is excavator is already digging some surface about 30-40 centimeters to see how depth they can occur. They can find the ruptures. Next slide. Okay, you can see this very clearly, and this right hand side, this was a watermelon field, so you can see the rupture is still there, so you can see the difference. It's already toward not only go to west, but also go to north. Next slide, please. And for bridges, I think we talk about a lot of this, and so I will just skip this one because you have more details. Next slide. For the rock fall in 60 stone, so we can see the very clear the rock fall pass. So I just keep elevation change in pass 1, the upper one, the big rock. The big rock we can measure in from the model in previously. I just give you 2, so you can measure in the biggest one. Rock is 4.5 meter by 4 meter and by 3.6 meter, and you can cut the pass profile to see, and for the pass profile is 1 by 1 meter, so you can see that it's not a very fast. It's not jumping. It's just a very slow rotation. It's not if the stone runs very fast though, so the travel distance should be more, but it stopped occasionally about 350 meters. Next slide, please. And the other is because I do the remote sensing because my specialist is landslide. So this is an Anton landslide site here. For internal landslide site here, it's not obvious rupture. No, rupture. You can see the drone. You can see from drone, but from ground surface, you can see a lot of cracks. So I drew an INSAR called seismic vertical deformation in the middle. So you can see the red, the red one means the subsidence is in elevation change to the lower, and as you can see, this 1/3 part of the landslide is especially the low part next to the river is sliding, and the other part is not so obvious. And the other interesting thing is the internal landslide site is landslide monitoring from soil and water conservation. You can see the right hand side is groundwater observation. So you can see the groundwater, and before earthquake, there are a few hours, you can see the groundwater level goes down, and after earthquake, the groundwater level it goes up very quickly. And after a few days, it dropped to normal. So that's very interesting. So I joined the internal landslide monitoring site this year. Hope to I can get more data from them. So that's a very interesting observation from the groundwater. Next slide, please. And also soil and water conservation, they have already released the landslide inventory map with optical image. As I mentioned, the INSAR the monitoring is not totally failure, but this map is a map with optical image. So they identify all the ground the surface change with optical images. So you can see that they don't have a very big landslide area. So you can see the maximum is already less than 3 hectares, and but it's open data, so you can download it from our government open data source. Next slide, please. So I could have a very quick observations. We have various drones because we have a limited time in 5 days, so we have limited batteries. So we use 3 drones, I think, and we have produced the drone also photos and DSN range from 2 to 6 centimeters. But so it's very valuable for your detail rupture identification, and the production was calibrate with GPP, and the error reduced to centimeter label 1 or 2 centimeter for horizontal, and a vertical to 5 centimeter, I think. And the rupture is the rupture can be observed with uplift from the fault slip, and Changliang fault, the right hand side, the upper one, is observed deformation not only toward west but north due to east. And the night rupture and elevation difference can help to construct earthquake model. And this is my presentation. I will be happy to answer questions. Thank you.
Thank you, Linus. And so for the last part of our presentation, my colleague Ben Mason will summarize the findings of the GEER campaign team, and we'll handle the Q&A question. Ben, take it away.
Excellent. So thanks everybody for attending today. On behalf of us all, we really appreciate it. Here's some summary bullets from the talk today that I think everybody here can read through. If I may go a little bit off script, I think there's some really interesting observations from a geotechnical standpoint. One is with the surface fault rupture. We've got a fairly complicated fault system with the central range fault being blind, and we suspect intersecting the longitudinal valley fault. And then we have a couple of fault splays with Fuley and Yulee faults. So we're trying to use all of our reconnaissance information to piece together an interpretation of how that faulting took place. And we're doing that with our Taiwanese colleagues. With respect to the ground motions, one thing that's very nice is the density of the stations, and also the fact that they were really along these faults. And so that's going to allow us, one, to piece together the surface fault rupture information, but also to start understanding things like the bridge damage, which you heard from Trevor. We were surprised at the lack of liquefaction through the valley, since it's an alluvial formed valley, but looking at the types of soils, there's a lot of cobbles, there's a lot of gravel throughout at least the upper surface. And we'll also note that the ground motion durations were very short, as you probably saw in some of the time series. We also think that the seismic earth pressures or the seismic earth pressure observations are very important. And so we look forward to performing more work and then presenting that information in the GEER report with the hopes that more people in the community can use that to further seismic earth pressure research. With respect to landslides, I think the slow moving landslides are really, really interesting. We see those all up and down the west coast of the United States and Canada, among other places. So I think we have a real opportunity here, especially with the drone footage that Linus and his team collected, to make some observations about slow moving landslides and how they can be sped up potentially during earthquake motions. And finally, I'd like to echo two other things. One is just the importance of drones for reconnaissance. I think we've come around to this view as a community, but we had a professional drone team with us the entire reconnaissance effort, and has made a tremendous difference to helping with our interpretations. And then finally, we were able, through the leadership of David Frost and GEER, to bring a number of junior faculty members and junior people in the field with us. And that has been an incredible learning experience, and one I certainly hope continues. So I think I'll leave it at there, Dominiki. And I think there's a couple of questions in the chat. The first one is from my colleague, Sean, and I think it's mainly directed towards Trevor. Trevor, do you expect local or federal Taiwanese officials to be able to use our results to assess the condition of the damaged bridges and or improve retrofit new construction? And so it's mainly a building code question, I think, and maybe talk a little bit about the US and Canada if you want as well.
Thanks, Sean. Yeah, I figured I'd answer the question here as a group. I think, yes, we're kind of, any of the data that we're generating, we're trying to kind of share that with our Taiwanese colleagues, both at INCRE and then perhaps at the governmental levels. And I think going into that is not only our observations of failure, but perhaps our processing of the ground motions itself. So thinking beyond necessarily what the structure failures are, but how did we reach that state, characterizing the actual demands of the motion and the deformation. So working with that, working with, thinking back closer to home here in the US and Canada, working with some of the building code committees, just trying to say, we can get these conditions with these large velocity pulses. What would that look like for our bridge structures? Are they adequately designed for this? And just, trying to kind of do an inventory of that for any place that has a directivity effect or concerns with these forward kind of moving pulses. So part of it, I think, is that, again, the direct assessment, but then also the combination of the ground motions and thinking about how everything plays in and works with each other.
Excellent. And I echo that, Sean. As you know, at the survey, I work a lot with the building codes. And so we're already kind of thinking about this in terms of interacting with AASHTO, for instance, in the United States. A lot of these bridges, you see very similar types of construction techniques in the US, and certainly in seismically active areas where you're going to have velocity pulses for quite a few in our country. We really need to pay attention. All right, any other questions? I think you have to type them into the chat. Maybe we'll give it another minute in case anyone is typing. And otherwise, I think we're right on time at ending at 2 Mountain, 1 Pacific, 4 Eastern.
There is a raised hand, but I don't know whether Jinshun Ni. I don't know if I said that correctly.
Yeah, I'm not sure if participants can actually talk. Well, maybe I'll ask the participant with the raised hand, you know, if oh, okay. No problem. So I don't know, Elliot, do you want to say anything in closing?
No, nothing in particular, but just thank you all for coming, and thank you to our speakers, obviously, and thank you for taking the time out of your day to present to us. And just a reminder, this will be posted on the GEER website and the GEER YouTube page. So if you want to go back and watch it, you're free to. Be on the lookout for some more upcoming webinars. Of course, we have a GEER team in Turkey right now, so that will be an upcoming webinar the next month or two, hopefully. Yeah, just keep your eye out for more GEER news, and thank you all for joining us today.
Thanks, everyone.
All right. Thank you.
Thank you.